Right, so we can start. And as I was telling you before, first thing first, some admin. I have set up group choice for project assignments. This is basically optional. So if you want to do the project by yourself, you need to select a group. But if you want to select to do a project with one of your mates, then choose the same group, and then the submission can be done by one of you, and everything will be graded accordingly. So the assignments are not yet visible for the projects, but they will be after today, at least the project draft. The project draft is going to be due on at the end of May, and you can look at it now. So basically what you need is a project title, a problem statement, so what you want to do, what the project description is, how the approach and methodology is, and what is the expected outcome, and what you're going to use of resources and tools of what we discussed in the class. So this is very detailed. The description is probably longer than what you need to write. I just need an A4 to understand, more or less an A4 to understand that you are on the right track. Okay. Of course, this doesn't have to be done by yourself in isolation. This is what the lab is for, to help you set this up, and also for the office hours. I mean, they are there for you to come and talk to me, or to Lucas about your project. So if you have questions, see if anybody else is joined from remote. Yeah. So any question also from remote on this before we move on? Due on end of May, should be quite easy. I mean, it's just about making sure that you are on the right track with the project. All right. So then the project itself is going to be due on the end of June, as we discussed at the beginning of the lecture. It's a pass or fail, so you submit the code here, you give a presentation afterwards, and that will be the admission for the exam. So that's if everything is fine, you'll be admitted to the exam, which we'll have to schedule. We'll do a poll at some point, or we communicate a date. We'll have to schedule it sometimes in August for the final exam.
Is there any recommend project?
If you don't have any idea by yourself, we can discuss something, maybe in the office hours or in the lab with Lucas. You can come up with a project for you. All right. So then let's move on to the lecture of today. This is the third lecture on high performance computing for cellular physical systems. So what we discussed last time were threads and also some metaprogramming, but from now on we'll be focusing on multiprocessing, and much of what you learn in threads transfer to multiprocessing as well. Before we go on, a short review of what we discussed last time. So threads are basically a nice tool to basically start and offload some piece of code to a different thread that execute in parallel this piece of code in parallel to your main process. Now, when I say execute, it doesn't really execute in parallel, but it's able to wait in parallel for example, I/O operations or other resources, let's say, that will take time to be collected. We also discussed locks, very important. So whenever you have a shared resources, for example, if you are collecting data from the internet and you're saving this data somewhere that might be then processed by the main thread, you want to have a shared variable where you save this data. Well, this variable has to be locked, and you have to be careful that you don't write and read at the same time, because you might get inconsistent data. To achieve this, we use locks, and what we do is we actually acquire the lock. It's like a key that only one process can have, only one thread can have. You take it. Once you have the key, you can do modifications or read the data, and then you release the key, and another process can take it. Okay, so this is a universal thing. We will see that there is exactly the same locks with exactly the same grammar as well in multiprocessing, so nothing changes, it's just that it's a different underlying structure that you're using, but it's the same logic. Then we've seen semaphores. We'll see more semaphores today. Semaphores are basically locks where you can decide how many processes can acquire a lock, and then stop it once this lock has been acquired multiple times up to whatever you decided at the beginning. So we'll see a very useful implementation, use case for locks today in what you call a producer-consumer pattern. So where a process produces data and the other process consumes data. And then we saw read-write lock. We won't see any read-write lock today, but it's a very useful concept where basically you have one process that produces data, and there are multiple processes that consume data, and this multiple process can run in parallel, but cannot run in parallel with the producer because otherwise they would run into an inconsistency. When they try to read, for example, a byte or a word from the memory allocation where the producer is currently writing, they might read inconsistent data. Or even if they read inconsistent data, nobody says that the writer is going to change that particular pattern of data. I mean, let's say it's an array while the consumer is still reading it, right? So it's going to be inconsistent at a higher level. We also talked about the global interpreter lock. So everything that we discuss with threads is bound to the global interpreter lock, which means that basically no thread is able to do computation in parallel to another thread that's doing also computation. So which basically tells us that threads are not the right tool if you want to do concurrent data processing. If you have a large array and you want to distribute this array for processing over several cores, you will not be able to do it with this. So we need another tool, a better tool, which is multiprocessing. Multiprocessing is different from threads, and mainly it does the same interface. If you naively look at it, it does the same things, but it's actually very different piece. First of all, threads are lightweight, are pure Python. They are internal to the interpreter. They are independent of which operating system you're using. They work always the same because they are pure Python implementation. Processes are based on the operating system. So when you create a new process, under your command to start the process or to create the process, there lies a call to the operating system that in Linux would be a fork, in Windows would be a spawn, and it's a completely different beast. I mean, it behaves also differently, and sometimes you have bugs because you tested it on Unix, but it doesn't work on Windows because the underlying library is different. Important is threads are lightweight. They are being a Python object. They can be started with very few overhead. There's almost no overhead in starting a thread. But if you start a process, it's not that it's simple. I mean, even for the computer, it takes some time, and so if you start a lot of processes, this might impact your performance. It's usually a good idea not to start too many processes, but to actually reuse them, to find structures where you don't have to start or close processes too often. Processes are not bound by the GIL. That's the very big difference. Since it's a completely different process, it has a completely independent basic operating system process behind. There is no GIL because the GIL is bound to the interpreter itself. There is another interpreter there, which also means that it's isolated and it cannot access the memory of the main interpreter. So if you have a global variable in the main interpreter and you start a new process, the global variable will not be available to the new process. You can copy it when you start it. It will be copied by value, and then you will not be able to access it anymore. If something changes, you will not see the changes. So this means that we need some kind of inter-process communication, IPC. And well, threads add shared memory, so you could have actually global variables shared across the threads without any problem, right? And also, all this thing means that it's very complex to set up. We'll see that you have to think ahead of what's going on a bit more than in threads. Threads are pretty simple in there. This isolation is also advantageous for another aspect. If a process fails, you will probably not bring down your full program with it because it's different OS process. So it might, die. You might be able to recover if you have in place mechanisms that check, for example, the process life cycle if it's still active. And if it's not, you might actually be able to spawn a new process to take over its job, right? But if the thread fails, chances are your interpreter is going down. And since you have only one interpreter, that's it, right? Or it's going to corrupt your data. I mean, global variables or anything that is shared with that. In the end, basically, the typical choices, if you have an IO-bound program, like for example, you're collecting data, you're scraping data from the internet, then you probably are good with threads. But if you want to distribute computing across machines or across cores, you want to actually go for processes. So far, so good? All right, let's move on. So how do we start a process? Process starts in exactly the same way as in a thread, with one little difference, and this is that instead of being called thread, it's called processing for multiprocessing, but the main difference actually is if name equal main. So this is very important. If you miss this, you're going to run into trouble. And the reason for this is that, for example, on Windows, where you spawn a new process, a new complete process for each time you do this, right? You do process and start. What happens is that this file is going to be read by the new process, exactly as it is. If I start P1 start, the Windows process will start from here. The interpreter with Python will just read everything again. And if you don't have this one, it will start a new process. And it will go on recursively forever, right? So you have to have this protection. And this works because Python, when you start the main script, it assigns main to name. When you start, for example, you import a module or you start a script through multiprocessing, it will assign actually the name of the file -pi to name. So you can differentiate if it's a main script or not. And this protects then the starting of the process itself. For the rest, it's pretty standard. You have your definition. If I manage to do this, you have your definition, then you have the process start, and then you have join. And as for threads. So again, we're going only through the basic API. There's more that you can do. You can terminate, for example, a process. If you think the process is not going anywhere, you can use terminate instead of join, and this will terminate the process where it is. You can restart a new one, and so on. There's a lot more to the interface that's just these three. But for everything that we do, we'll probably use just start and join, nothing else. All right. Another big part of processes is that we don't have global variables, right? So we have to be able to share memory between one process and another. And there are a few primitives in multiprocessing that are very useful for this. And in particular, here we're going to look at array and value. So what do these guys do? They basically wrap the variable that you have in your local process in a shared memory and make it available for other processes to use, all right? So I'm having two examples here. One is an array and one is a Boolean. Let's look at the Boolean first. So I define this shared value as Boolean B, false, initial value, okay? So once I've defined it like this, I can actually access it from a thread that have this pointer. So I pass this from processes that have this pointer. So I pass the name, the term, which is basically a pointer to memory, and then I can access this with .value, and I can change its value in the shared memory. So if I change it from one process, I can access it from another process and check its value, right? I can do this like this. For NumPy arrays is a bit more complex. I mean, we'll see NumPy extensively, but in this case, it's a very simple application. We just have one-dimensional array, 1, 2, 3, 4, 5. And we just define a NumPy array by just wrapping NumPy array on top of the list that we have from Python. So we define this as a simple NumPy array, and then we define on top of this a multiprocessing array, which basically wraps the NumPy array as a double C-type array in shared memory, and you can share it now with other processes. Okay. In the same way that you access this by value, if you want then to reaccess this one from NumPy, you use this MP from buffer. MP from buffer basically takes the object in memory and wraps it in a, let's call it a mask, a view on top of the memory. So it doesn't copy it to your process, but it really just has a set of pointers in NumPy to each element on the array, and you can manipulate directly the shared memory from this NumPy object in your process, right? So it avoids, for example, if you were to use queues, which exist also in multiprocessing, I will see them, it avoids copying data. Once you created this array in memory, every process can access it where it is without the overhead of moving it to the process, moving it back to the shared memory. Is this clear? Fantastic. Then we can move on. And we'll move on to a demo with this. So this is an example of writing and reading data from an NumPy array like we just defined above, right? So let's go through it step by step. First define the array in our local main process. Then we define the wrapper around the array itself. We define our Boolean. We'll use this Boolean to communicate that there is no data to read anymore, right? So we'll set this to true termination when we're done with writing data. So we tell the reader that he doesn't have to wait anymore for data to read. And then we have one condition to protect this whole thing. So now we start to process. One writes the data, one reads the data, then we start both and we join both. So far so good, right? So what we do is, to start the process, we call target with the function that we want to call, and then we give the args as a tuple with everything that we want to pass to the process. And here we pass all the pointers to the shared memory object, like array, termination, and condition. So every lock that you want to use, every condition, everything, every shared memory needs to be passed here. Then you will not have access to this process anymore. Once you have initialized it, you need to have all the tools to access the shared memory. That's why it's usually something that practices to start all your processes as the first thing in your program. You first set up your network of processes and how they communicate, and then you go on and do your stuff. You don't, for example, pre-process the data, do other things, and then start the process when you need it. It's not a good way to do it, because it's, first of all, it's a overhead. If every time you need it, you need to start the process, so you want to start them early and keep them around. And the second point is, it's very good to know and document right at the beginning how your network of process works, right? So, questions about this? Also from home? All right, so let's move up and let's look at what happens in write, in write, I'm trying to scroll the editor from here, doesn't work, right? In write and read data. There we go. All right, so what are we doing in write data? First of all, we are going to take the array that was passed to us and read it from NumPy. So again, as before, NumPy from buffer get object. So this is not a copy. It writes to the original array in shared memory. Then I'm just going to start my process in writing to this array. To do operations on the array, right? So this is just something that it's a test, so I'm just doing a loop of 2, sleeping 1 second to simulate the time of writing. And then what I do is I pick a lock with condition, like we saw on the thread. Do you remember condition? Condition is a lock, basically, that makes it possible so to notify other processes that have the same lock. And when you wait on condition, it releases the lock. When you notify, it tells you to reacquire the lock and process the data. So there's this double functionality. You can both notify other processes, like an observer, and at the same time, it's a lock when you're not waiting on it. So with condition, I'm going to increase every element of the array by 1, and then I'm going to notify the reader that it's time to read. Good. Then I sleep again after the loop. After the loop, I sleep again 1 second, and then with condition, I terminate the reader. The terminate value equal true, notify, so that the reader knows there's nothing more to read, can exit. Because otherwise, the reader will just keep hanging. It will keep waiting on condition to do something and try to read from the array. There's nothing left to read, right? So we need to tell it. Doesn't have any other chance to know that we go. I mean, the producer is always in control of the process. So the producer will decide what to write, when to write. The reader, the consumer doesn't have any chance to know what we need to do unless we tell it. So we always need a channel of communication. And this is one. It's the other. There's events, there's queues, and so on that we can use. So far, so good? Good. Then let's go to the reader. When you read data, right, again, look at the shared memory and create a NumPy array. This is just something to show you how to save data locally, but I mean, important part is here. So same with condition, we always take the lock on the condition. While true, wait for the condition to activate. When we get the notify, we check. Actually, that was smart. We check that the array is not equal to the other one, otherwise we just don't do anything. And otherwise, we consume it. I mean, this is just a print change, but the point is, this operation is basically consuming the data, checking that something can change and do whatever it needs to do, right? And then I just copy it back to my local data. Also, the next thing that I check is if the terminate value is true, then I break. All right. So this seems to be fine. Shall we run it? All right. Seems to be pretty all right. What happens if we remove the time slip? What do you think? Have any other sleep? All right. What's going on? Same code as before. I'm just not waiting 1 second. But it's not printing anything. Let's try again. Nope. Oh, now it's printing. Wait. Now it's printing again. Now it's not. What's going on? Let's try to do some debugging together. Any ideas? Try to follow mentally. Let's start from here. What is happening here? What's the first thing that happens? Go down, start the process 1, start the process 2, write data, read data, and write data is here. So somebody follow through and tell me what's going on. So I'm inside the range, pick the lock-on condition, increase the value by 1, and notify. At this point, what would happen once I notify the condition? Will my reader pick up here or not? You expected to pick it up, right? You expected the weight to actually break because it's been notified. Why could it be that it's not picking it up? What could have happened? I mean, if somebody says if the probable is not is being excluded, then we must look at the improbable, right? So why could it not be waiting? If it's not, if it's not executing, it means that it's not waiting, right? Because otherwise, if it's waiting, if it's here, and the notifier arrives, then it will process the data. There's no other way. This is, this is code, right? It should work like that. So if it's, why it's not waiting? What is happening? Think about it. What could it be? Let's put it this way. Before it was waiting, and we were sleeping 1 second, and then notifying the process. And the process was there waiting. Now we are not sleeping 1 second, and the process is not waiting. We're being too fast, right? So it means that this process is not yet here. Right? It's a timing issue. You start two processes, one is faster than the other, arrives to notify, while the other is not yet at the wait. So the process is hanging at this wait, nothing happening, it just stays there. And actually, in the cases where it's hanging, like here, it's not even picking up the second change or the third, or the terminate. It's not picking up anything. The process, the write data is finished before the read data actually arrives at condition wait. So these are pretty nasty bugs to clean up, right? If you are using multiprocessing, it's a good idea always to design your process so that these things cannot happen. That you don't rely on timing for your process to synchronize properly. So you want to have a mechanism that until this guy has arrived here, is keeping this, whatever mechanism you have here to start the process, is keeping it alive and waiting for the process to actually ask. This could be a queue, for example. If you had a queue instead of a condition, the queue will keep the command that you send through the queue, and once the process arrives here and gets from the queue, it will be there, right? But with a condition, it's not. Depends on time, right? So in threads, you usually don't see this kind of bugs because threads are very lightweight. So the timing to actually start the thread is minimal, but it is the same. Would be the same bug also with threads. If you slow down the reader and you increase the speed of the producer, then it will actually bug out. We will actually go into a deadlock. Usually you don't see this because, if you're producing data, it will take time to produce data. So you start your reader, it takes 15 nanoseconds on the thread, and then your producer is reading data for half a second and then sending it into the condition notifier. So you'll never see this kind of bug. But you are running on an assumption, the assumption that your reader is actually faster than your producer. And there could be ways where this is not the case. Let's say that you are reading something from the drive to configure a reader, right? A configuration file. And this file system, which you expect to be many times faster than processing your data, in 3 or 4 seconds, is not, because it's a cloud-based file. Then you're waiting for a second for the configuration file to start. The reader is not active, and you pass it by, right? So it's not just being very attentive to bugs that will never happen. This is actually something that can happen a lot of times. So don't rely on time. Always find a structure that is 100% sure to process your data whenever you set it up. So now we have to stop it. And you can look at all the nice forks and so on that it's doing, but not interesting right now. So how do we make this particular program a bit more stable? One thing that we could do is use queues for synchronization. So the basic idea is that we have a queue in between these two guys, between the producer and the consumer. Right? And what we do is we use a lock to produce our data, then we release the lock. At some point, we put something in a queue, and the consumer is waiting on this queue. Once the queue has a value, it will lock the data, right, that I'm producing, and consume and release the lock. At the same time, the producer can go on and lock a second resource, for example, and keep producing data, right? It doesn't have to wait, doesn't have to be sequential, otherwise it's purpose. You don't want to do it sequentially. But what you can do is you can actually pipeline your data by using a queue to synchronize the two. So whenever you have something new to give to the consumer, you put the index of whatever you want to do. For example, it's a big array and you want to go line by line, right? You put the index of what you want the consumer to get in a queue. The consumer reads it from the queue and that starts its work. So there's no risk that it misses it because it will wait on the queue or the queue will wait on it. Whoever's arrives first will wait there, right? But the producer can go on. Once it queues the index, it will go directly. It will not wait for the queue to be collected, for the queue item to be collected. Is it clear? Shall we look at one implementation for that? If I find it. There. So all right. Let's remove this crap. And let's look at what we need to do this. So first of all, the setup is quite easy. So I'm using what is called a double buffer. So I have, I don't know if you are familiar with video cards, how they work. When you write to the screen in a video card, I mean, since a long time ago, you don't write directly to the screen, you write to an in-memory array, and basically the screen switches between two arrays. When you prepare the first, you look at the second. When you finish preparing the first, the screen will switch to the first and you will start preparing the second, and so on. And you keep switching so that your screen is stable. You don't change the pixel while they're displayed on the screen, and at the same time, you have time to prepare your array. So you do this double buffer. This is very convenient if you have a consumer and a producer and you have large data. You can start basically writing to an array, and while you prepare this array, the consumer will consume the second array, and then you can switch to the second array, preparing the second array, while the consumer consumes the first array, and so on. So what I'm doing here is I'm creating two arrays, data 0 and data 1. Oh, a queue with a limit of 1. So whenever I put an index there, would not be able to put a second index. So if the array 0 has not been yet consumed, I will not be able to put array 1. Right? So I'll be blocked by, I cannot put more than 2 arrays in a loop, so to say. Okay, so again, I process 0, queue 0, process 1. This is the producer, okay? And then I want to queue 1. Now, the consumer will get 0 and consume 0. And before it does this, I will not be able to do this. So I can produce 2 arrays, but I cannot go back to the third and produce the third. Right? So we'll come back to this. There is a bug if you're not careful here, but we'll see it later. Actually, we'll see it in action. So I create my 2 NumPy arrays. I create 2 arrays as we did before, 2 multiprocessing arrays for shared memory, and I pass them to the 2 processors. array 0, array 1, and Q. All right, I don't need anything else. Good so far? Start the processes and join. So let's see how we actually produce the data now. Can somebody explain to me what this thing is doing? This line of code? You remember these comprehensions? Remember, this is basically array 1, array 2, right? These are the two shared memory objects. So now I want to apply from buffer to both A1 and A2 and refer to it with an index. So the best way to do it is to np from buffer to a get object for A in array. Right? So I'll apply it to both and I get back a list again. Right? Now I save it to arrays. Now I can refer to my NumPy arrays by index 0 or 1. Clear? This is if you don't understand this, we can discuss it more. I mean, this is first time you see NumPy, and we haven't seen this comprehension in 2 weeks. So, any doubts about this? All right. So then I start producing my data. For index in range 5, I mean, this is a completely arbitrary. What I'm doing is I'm picking a lock. Now this is quite convenient. Array comes equipped with a lock. So I don't need to define my own lock. I can actually use R, this one, right? My index, get lock. So the shared memory array comes equipped with a lock that I can use. If I do atomic operations on the array, the lock is automatically used. For example, if I do, if I use this array and say array position 0 equal 1, I don't even have to take a lock. This is already protected. The problem is that I'm using here a lot of operations in this one single line. Increasing by 1. We saw that before. Plus equal 1 is not atomic because I need to read the value, I need to increase the value, I need to set it back. These are 3 operations. Moreover, this is on a full NumPy array, so it will increase every element by 1. Which means it's more than 3 operations. It's actually n times 3 operation, right? So this is definitely not atomic. Then I need to take a lock, and I'll take directly the lock that is provided to me by the array. Clear what I'm doing here? Okay. Just printing, and then I put in Q my index. So I'm telling my reader that the array is 0 or 1, I mean index mod 2, right? Either the array 0 or the array 1 is ready. Done. When I'm done, I'm putting the value -1. This is typically called the sentinel value. It's a value that doesn't occur in my data, that I know as a convention that when it arrives, it's over. It's called sentinel. Any question on this? All right. So next up, read it. You can read that. So when I read the data, I do exactly the same. I set up my arrays, and then I just wait until I get a new index to read, Q get. All right. So once I get this, I check if it's a sentinel value. If it's a sentinel value, I break. It means that the producer told me to stop. But if it's not, I need to acquire the lock the specific array before reading, and then I can just consume it. Right? So this is, I mean, this is a very stupid consuming routine, but it just prints the index and the value. And before doing that, it sleeps by 1. All right? So we can run this, and we'll see that there are 5 times produced arrays, increasing in values, and then 5 times consumed. The arrays will be 1, 2, 3, 4, 5, then 2, 3, 4, 5, 6, then 3, and so on, right? Then to 7, and the other one will go 6, 5, and so on, increasing every time by 1. Nothing spectacular. Okay, produced 2 at a time because we have produce and consume 2 at a time because we have this leap 1 inside. Everything is done perfectly, and in the end the process stops. So now, since we have this nice cube that stops at 1, one thing that I wanted to ask you is, do we need the logs? Do we need this? What could go wrong? I'm only queuing 1 index at a time, right? So let's think about the process. The producer and the consumer. So the producer produces 1, then queues 1, then produces 2, then produces 0, then queues 0, then produces 1, then queues 1, and so on, right? The consumer will get 1, consume 1, get 0, consume 0. When is get 1 happening? After Q1, right? When is Q0 happening? I mean, after it produces 0, but also after get 1 has happened. Because the Q can only contain 1 value. So until the 1 has been taken from the consumer, the 0 cannot be queued. Right? And when is the processing 1 happening? Right after. It doesn't have to wait for anything else. So what can happen is that process 1 and consume 1 happen at the same time. Right? And this is, again, a nasty bug because it depends on the time. So shall we try? Let's remove the logs and see what happens. Oops. Wrong comment. Too much LaTeX later. Oops. That was not what I wanted to do. There. Produce 0, consume 0. Took the second value, not the first. So it actually missed 1 value because we didn't have the log. So Q doesn't protect you from that. You need to, again, be careful, your mechanism, how to synchronize it, because if the consumer takes longer and you keep scheduling, even if you have just 1 index, in this case, you will basically run into an inconsistency problem. It not be a deadlock, right? So your program will run fine. Everything is okay, but then the results will be wrong. Understood why it's happening and what is happening? Still clicking here instead of here. All right, so we cannot do it without logs. Keep the logs. There is another way we could do this, and it's using semaphores. Let's look at it. We're going to use 2 semaphores, one for full buffers, one for empty buffers, right? So the main idea is that if you want, we start with 2 empty buffers, of course, right? There's nothing, nobody has written anything there. So the main idea is that the producer will acquire an empty buffer, produce the data. So what I mean acquire empty buffer, it means it will remove one from these two, will decrease the semaphore here by one. All right. So acquire an empty buffer means empty is equal 1, okay? Or minus equal 1, let's say. Then we'll produce data, and then we'll release a full buffer. When I mean release, I mean that this semaphore here, full, is going to go plus equal 1, right? Now, the consumer on the other side is going to do exactly the inverse. It's trying to acquire full, so it's going to do full minus equal 1. But since full is 0, will not be able to do anything until the producer has written something into the array and as well into the semaphore. So once the semaphore has been released by the producer, the consumer will read the semaphore, will acquire it, and will start consuming the first index. And then it will release an empty. So it means that empty is going to be plus equal 1. And so on the other side, once, let's say the consumer is very fast, it will write 2 buffers, right? But then the empty will be 0. So we'll not be able to acquire anything until the consumer is finished with the first one and release another empty buffer. Then the producer will acquire 1, so we'll go back to 0 and we'll start filling again. Now, whoever is faster will actually manage to deplete its part of the semaphores earlier. But the 2 semaphores will actually protect from something like we had before from happening, right? You get it? It's not possible because there's always need to be an empty buffer for the producer to write. Otherwise, it will just keep waiting on the empty semaphore. Any question on this? Shall we see an example? Wrong? Yeah. All right. So this is a bit more involved, and actually, for this case, queues are probably more immediate. There's a lot more going on here. But I think it's interesting because it shows you how you can use semaphores intelligently to keep track of what's going on and to start counting down and counting up who's using what. So what we're setting up is 2 semaphores, full starting with 0. This is basically the initial count, right? And empty starting with 2, right? So this is how we manage how many buffers we want. We could actually have 3, and you know, if you had a different architecture with maybe 2 consumers, you want to have always 3 buffers active, 1 for writing, 2 for reading, you could do it like this. Then we have a new kid on the block, which is an event. Now, an event is a shared variable that you can use to signal another process. So basically, what you do is you set it at some point, and the other process can check if it's set. That's it. Nothing else to it. It's another way to terminate without queuing something or using a shared variable and locking it, unlocking it manually. It's already done for you. And then I have 2 locks set up to use as a lock for each of the array. This I'm doing it manually. You could do it actually with the get lock from the array, just to show you another way to do it. Nothing else. I mean, this is as before. We just define the data, share it in memory, create a process for write, create a process for read. We pass all that we need to pass, like the 2 array for the data, the 2 semaphores full and empty, the terminate event, and the logs, right? So everything that we need. Then start and run. So, and here we're going to write the data. So, write data, again, array, full, empty semaphore, terminate event, logs. Logs, not single log. I don't know why I wrote it. I wrote it singular. So, For the arrays, we do the same as before. From buffer in list comprehension, we get each item from the shared array and we transform it into a NumPy array. Then we start with an index 0. Now, the index math in this case is not done by queue, it's by convention. I say that I start with 0, and the reader will also start with 0, but it's not signaled in between, right? So it's basically by the fact that if both start with 0 and they go to 1 and they go to 0 and they go to 1, it will be synchronized. You don't have to communicate. Here is where you write the data. So first of all, we acquire an empty buffer. So if there is no empty buffer, we sit here and we wait. But there are 2 at the beginning, so we'll actually go two times through this. With the lock on this particular array, so this is either 0 or 1, because I change it here, index equal 1 minus index, right? So if it's 1, this was going to be the second lock. With this lock, I'm going to increase, as I did before, all the values of the array, and then print it. And then, important, I release a full buffer. So I acquire an empty, I release a full. Because on the other side, it will be the other way around. Okay? And then I switch my index. I flip my index from 0 to 1. Clear so far? You notice already that this code might be actually smart, but it's a lot harder to read than the queue. The queue is very logical. You put something in the queue, you process it on the other side. You have to keep in mind 3 different values that are flipping value, and you need to understand what it means, right? It's all by convention. So while it's very, very nice as code, I still prefer the queues, because if somebody else reads my code and it's structured with a queue, it's evident what it's doing. It doesn't need documentation. If for a code like this, usually you need to explain. I mean, this is a very simple example, but if you use this kind of structure, people will say, what's going on, right? Oh, by the way, we'll see this. So the read data. Read data, same story. I acquire my data, my arrays from the shared object, and I wrap them in a NumPy array, and then I set my index to 0, because I know that the first buffer is going to be the 0. And while not terminate is set, okay? So if the process has not been terminated, then what I do is I acquire, we'll see why, but ignore for now block through and timeout 1, okay? I acquire this full block, and then if it's positive, this is, let's say you just do this, okay? Ignore this part, say it doesn't exist. I acquire the full log, I process the data, and I release an empty. All right? Now we're going to see what's this old business with the timeout and the blocking and so on. And we're going to test what happens if we don't do it. All right? But so far, this is clear, right? Acquire empty, release full to produce the data. Acquire full, release empty to process it. You empty it, you release an empty one. And then we just started everything and so on. So, what's this business about determination? Keep trying to scroll there. So, when I want to terminate the process, first of all, I should check that my buffers are empty. If they're not empty and the process is still processing and I send in the termination event, I might risk that in the while loop below, here, the producer has put 2 buffers to process and then terminated. He will go through here, processing the last buffer. It says still 2 buffer, filled with data, but it says the terminate has been set, so it will just go out. Will not wait and will not process the last 2 batches of data, right? They're clear. All right. So then the next part that is annoying is that if I set the where is it? Here. If I set the you know what, let's try it out. So let's remove the if here, and it's easier to show it than to explain it. Delete a bit too much. No timeout. And let's run it like this. Seems to be working, right? Produce, consume, produce, consume, produce, consume, but it's not exited. So what's going on? We have produced and consumed everything and worked so far very well. But at some point, it got stuck, right? So I can tell you that this full acquired is not going to be able to find the full buffer, because there is no full buffer anymore, right? So it's waiting here for a buffer to be full, because in the meantime, the writer has finished with these buffers, has written all the full buffers, and has sent the termination. Has done this. But we missed it because we were waiting, because the producer was waiting for an empty acquire. You understand? The reader has finished reading and then has released an empty buffer. All right? So the writer has been waiting on the empty buffer, on the last empty buffer, to be able to terminate the process. And once it received the last empty buffer here, has set the event to terminate to set, to positive. In the meantime, the reader has already gone through this, and now is waiting on full. But there's not going to be another full, because the only thing that's happening now is terminate set. Full was already at 0, because otherwise empty couldn't be set, and therefore you're in a deadlock. Got the point? So how do we solve this? And basically we just Ctrl Z or our way through this, and I'll explain what's going on. That was it, right? Yeah. So is there need something more? No. All right. So what I'm doing is I'm trying to acquire full, but I'm doing it with a timeout 1 second, because I know that usually it will just acquire, right? But if I am at the end, I'm actually being the deadlock. So in this case, I just give it a timeout and then check the value. If I wasn't able to do it, I go again through the while not set terminated set. This solves my problem. And since it's only for the latest process, I'm not actually losing anything. Because usually it will be wait here for 1 second, then it will go full cycle, check if the terminate is set, and then go back to waiting. This full cycle, if this is false, it's going to take with some nanoseconds, nothing more. So you check terminate, few nanoseconds, and then we'll go back to waiting on the full buffer. So I didn't lose anything, but I have this catch-all when my process with my producer has finished sending data, so that I can actually go back and check the terminate. Make sense? Sorry. All right. So again, you see, it's a bit more involved multiprocessing. You have to take care of a lot of different problems. And one of the things that help a lot when you're debugging this kind of bugs, problems, is actually to play with the timing of your processes. As you see, some of these processes don't happen if you actually increase the timing of one process or decrease the timing of the other, and then start to happen when you do the other way around, right? For example, if I had here between the empty release and the while not terminated set, if I had put a nice sleep, 10, I release the empty, the producer will be able to read it, put the terminate, and then I'm still waiting. Then I will check the terminate, and basically I'm done. Why is not the safest option? Because I'm relying on timing, right? I don't have something that is 100% sure to work, and something that in most cases will work because it will take less than 10 seconds for the producer to do his checks. But if for some reason somebody changes the code on the producer side, then I run into a bug. It works now, it might not work, down the road. It might be dependent on timing conditions on the resources that the producer is using. You never know. So it's an assumption. Instead of working an assumption, we can set something that works all the time. And then what you can do is you can start putting sleeps here and sleeps there to test that your code works all the time, that it never goes into a deadlock. Right? Okay. So this basically does it for producer consumer. We're going to see another way to share memory, which is a bit more direct. So array is good for simple examples, but array is bound to only one-dimensional C types. It has its own lock and so on, but usually you don't. If you're using NumPy with multi-dimensional array, you cannot use it. So what you usually see is you use directly shared memory, which is a lower level system. Shared memory allocates just memory for you. It doesn't do anything. Just tell it how many bytes you want. That's it. And must always be locked. Even if you do atomic operations on it, you always need to lock it because there is no protection at all. And supports any type of array in NumPy. So how do we set it up? If you want to use shared memory, you basically have some help. You don't have to do the computation of the bytes by yourself. For example, you can use size, NP array, and bytes here from your array. So what you do is first you define the data, right? So you have a prototype. From this prototype, NumPy tells you how many bytes you have. So you can actually tell share memory how many bytes you want and if you want to create it. Once you have allocated the shared memory in memory, then you can wrap it with the NumPy structure. So this is the second NumPy array now. This is wrapped around the memory that you have in memory, right? And then you copy your prototype into the shared memory, right? The first time around, you first create it locally, use it as a prototype to know how many bytes you have and so on and so forth, and then you put it in memory. If this is too much computation and you're dealing with terabytes of data, you might want to do the computation for the n bytes by yourself and generate it directly online. But usually this is just one time, right? So if you're processing images, say you got a camera and you're processing images as they come in. You take the first image, you save it locally, you create the shared memory, you copy the image to shared memory, and then you forget about it, and the second time around you just write it to shared memory. Right? So this is just a one-time thing. It's clear what's happening here? Alright. So how do you read from shared memory? Well, pretty easy. You pass the shared memory pointer or name to the process, and then you use this initializer, shared memory.sharedMemory name. Now you have access to the shared memory, and then you wrap it into a NumPy array, as we did before. So ND array, dimensions, type, buffer. You don't use from buffer, you use this, it's the same. Questions? So the difference with array is that you can do this for any shape, and that it's not protected at all. So up to you now. So while it was good practice to use locks with shared array, now it's really required. Going to also see another example with a process pool where we use shared memory to process a big array line by line. So what we want to do is we have, let's say, a very big array, and we want to process it, on multiple cores. So we start a pool of workers. Each one can update the array. But they will do it at the same time. And we will organize it in a way that they don't basically step onto each other's toes, right? So we'll divide the data and we'll assign different data to each of them. So how does a worker pool work? Instead of managing all of the processes yourself and starting all the processes with start and so on, there is some machinery that does this for you. So you can basically define a function, init a worker pool, and then dispatch this function, which is a command pattern, right? So you put the function and the data in one single object and you dispatch it to each worker with its own. They do it with their work, and in the end, you're notified when all of them are done. And this takes one line of code, right? Instead of doing a loop and starting the process and so on. It involves some machineries. Let's look at the demo first. Time, so we have 20 minutes. Process pool. All right, so starts to be a bit more complex, but it's actually simple. We work it step by step. All right. This is where we start reading the code, right? Whenever we have a multiprocessing program, ignore all the function, check if a name is main, and then you'll see the initialization. So what we're doing is we're initializing a random array, and then we are initializing our shared memory by checking this array size. We are wrapping this shared memory with another MP array, and then we're copying the value from the original array into the shared array. Clear? All right. Then what we're doing is, this is a context manager for manager, which is something that helps you set up inter-process communication as well as process pools, and pool. Pool takes num workers. So this already sets up your process pool with a certain number of workers. You just pass it as a number. We can decide it up here. There is a variable num workers. I set it to 2. You can change it later and see what happens. So you get the shared memory name from the manager, right? And just take it as it is. I mean, this is just a value that you need to get from the manager to be able to share the name across the processes. Start time is just for us for timing, and then it all happens here. This basically takes the pool and then use map. Map assigns something to something else, to a list. And you assign basically the function worker, which we'll see above, and then you assign it to I, a loop in range num workers. So to let the worker identify who he is, right? You pass it a number so that the worker knows I'm the worker number 1, I'm the worker number 2, and so on. And then you pass it the shared array. So we have a big matrix, and we pass the big matrix to all of the workers, right? But then we have numbers 1, 2, 3, and so on, and the worker gets one of those. So it knows where all the data is, but it knows also how it should work with it, because the number will tell it which lines should it operate on or not. All right? Is it okay? Do you understand what is this call is doing? This is the most important part here. Right? So the poll gives you the possibility to map a function to a set of workers by just providing the array of arguments. Right? Good. This is just bookkeeping, and we're done. And this is just for checking if the result is okay and so on. We can ignore it for now. So let's go to the worker. The worker will first read the arguments that we pass to it, like this. So I and share name from args. And then we'll initialize the array as we saw in the presentation, right? in the slide. So we'll first take a handle on the shared memory and then wrap it with a NumPy array by using this existing shared memory buffer. right? This is what we saw before. Then it has its own convention. So the convention is, for example, that I just go through a range starting with I. I is my index, right? So for the first worker is 0, for the second worker is 1, for the third worker is 2, and so on. And it will skip two lines every time, because num workers is 2, and it will go until the end of the array, until the end of the lines of the array, right? So the first, if this is the array and we have 2 workers, basically the first worker will go line 0, line 2, line 4, and so on, and I can use colors. And the second worker will go at line 1, line 3, line 5, and process the odd lines, right? Do you notice something missing? I'm writing on this array with 2 different processes. What is missing here? Anyone? What do you need to do if you write to a different variable with multiple processes? Lock. Why there's no lock? This works. And this, there is no race condition here. Why there is no lock? Any clue? Any ideas? So what's going on? My first worker will start writing to the array. What will it change? This one, right? So anybody else accessing this part of the data? Is there anybody else accessing this shared memory location? The second worker is actually accessing, I switch the colors around, is actually accessing this part. And then this part. But never the lines where the first worker is. As I'm alternating lines by lines, I don't need to acquire a lock on the full variable. I can do this in parallel without actually caring about the locks, because my data structure and my algorithm are so conceived that I don't need to be careful with the locks. Because the memory allocation is constant, the array has fixed length, and I can change the elements inside the array without acquiring a lock, because nobody else is accessing those specific bytes. Clear? So that's another way to actually organize your code in a way that is safe, thread safe, process safe. At the same time, it's performant. Because if you had to acquire a lock, I mean, then you cannot do it in parallel anymore, right? So how do you do it? It's not possible. If you want to do it in parallel, you have to do it in a way that you don't need a lock. Does it make sense? And if you could say, well, I can put a lock per line, but it's useless because nobody else is accessing that line anyway, right? So let's see another aspect of this. We have two workers right now. It's a pretty big array. It's 80,000 columns by times 20,000 lines, right? So I'm gonna start it. I'll take a couple of seconds to go through. Fully. Right. So the worker 1 took 1.14 seconds, 1.17 seconds for the worker 2. The whole process ended after 1.48 seconds. What will happen if I run 4 processes? Let's take bets. The worker, will it be faster? That's half the data to process, right? Because we have 4 workers, same number of lines, so we'll have half the data to process. Probably be faster. And the whole process? Let's see. Something. Like we had like 1.4 something, right? 1.4, 1.4, 1.7. Alright, so it's alphabet. And the process is actually a bit faster as well. Let's go to 8. So it's actually useful. I mean, I had the read processes, I had more cores, and it's actually going faster, right? Or is it? This is again half, right? Workers are half, was 0.6, now it's 0.3, a bit more than half. There's some overhead. The process is still 1 second. Not really that much slower, right? So there is a overhead to all this engineering in processes. We started with 1.7 with 2 processes, and if we put 8 processes, we are not at 0.3, we are 1.0. So we didn't win that much. I mean, of course, if we put more data in, this overhead will going to be less and less relevant. But be mindful, because if you have, again, this idea of starting processes whenever you need them and using a process pool for something that uses 2 or 3 seconds of processing time, you're going to pay a lot more overhead than what you're actually getting by parallelizing the whole thing. You might actually do it in one single core, it might be quicker, because you don't have all this overhead per se. So, lessons learned here, right? So, if you have to process 2 hours of data, yeah, it makes sense. You have to process half a second of data, no, it doesn't make sense. And if you have to process half a second of data in a loop, it's actually very stupid to actually start the process again and again and again. Yeah, I think we're done with this. Right, any question about this? A process pool in general, or shared memory? Last topic for the data, which is multiple consumers. So this is something that we already started seeing, but a typical way of structuring your code when you have to distribute data is to have one producer that actually, for example, is your camera, or another physical system that produces data, right? Then, when you want to consume it, you might actually want to parallelize things because they're basically too heavy to be done on one single core. So, what you can do is you set up a queue, right? And then you have the workers pick up stuff as they come. Because you don't have the luxury to do what we did before most of the time, to just map a process to a process pool and then have the data up front. Sometimes the data arrives as it arrives. You have to queue it, and then you want somebody to, in parallel, to pick it up. The first worker that is free picks up the next and keeps working, and so on, right? You don't want to keep track of the orders or so on. You just want this system to work. And this is the last example we're going to see today. Multiple consumer. So, which is actually quite simple one. So let's first go. In this case, I structured with the main function just to show you, how you can do it this way. But it's nothing changed. So if main start main function, the main function is defined. But until you call it, nothing is happening, right? So what is going on here? First of all, who is worker? Worker is the function over here. If you don't do it this way, it will complain. You have to pass the function to the main function like this, right? Because otherwise it will not find. But quirk of Python. But the main important logic is here. So this hasn't changed. We define a random variable. This is the same problem. We want to process the lines of this variable, of this array, line by line, okay? But the idea is that our producer just queues the lines, and the workers will pick the line as soon as they're finished with the last one, right? So we don't have an agreement of which one is doing which. It's just we know that they're working only on the line that has been queued. And that line is queued only one time by the producer. So do we need the lock? No, exactly. All right, so same as before, we define the array. Then we define a queue, and we define it with a queue depth. Now, this is not necessary, but if you have 20,000 lines, you don't want to pipe 20,000 lines in the queue because it's just a useless waste of resources. So we set the queue depth at 8, for example, or 10 or 20, so that when this is reached, then the producer will not be able to queue more lines until somebody has taken one. Right? So we keep an healthy buffer of lines to process, but not anymore. This is all fake. Usually, you will have a natural limit on the amount of data you can produce in queue because your sensors will not be able to produce millions of lines in one go. But I mean, just as an example. So then we start our workers. This time we cannot use the pool, so we start the process with target our worker function, arguments, the queue, and the memory name. So we just give it a queue where we tell you the index from here, and we tell you where the array is. And then we just start at for something in range num workers. Now, if you haven't seen this, this is a variable basically that tells to Python, I don't care about this variable, so don't bother me, editor, that I never used it. Because otherwise the editor will say, you define a variable, but you didn't use it, right? And we'll put the yellow line under it. So this way it will not. Then we loop through the workers, we start them, easy. And then we dispatch the line index. 4 line in range, queue put. Now, this queue put will wait actually when the queue is full, and it will block the process until the queue has gone below the queue depth, and then it can put a new one. So it actually is a way to synchronize also the main process to the workers. Once it's done, we'll put none into the queue. Might have a bug here that I just saw it now, but we'll see. All right, so far so good. Known is our sentinel, right? Sentinel means we terminate the workers with this. All right, so let's go down, up actually, the workers. Yeah, we can define new num workers and queue depth, of course, but also in the workers, very simple. Same as before, we access the shared data. Nothing has changed. So first we access the buffer by shared memory name, and then we put we wrap it into a NumPy array with width and height as we did before. Then, while true, we get the line index from the queue. First set. This blocks, right? Until there is no line index there to be processed, it will block the process, and we will wait on the new line index to be there. Once we check if the line index is known, break. And otherwise, we just square every element in the line. As simple as that. Once we're done, we close our shared memory and we record the end time. Right? Very simple, right? Good. Let's see how it works. Good. So, seems to be working fine. In the end, we had more or less the same time, one something. But it was not as efficient as the other, because there's a lot of processing in the queue going on and on. It's a lot more overhead than the other algorithm, right? You're doing a lot more bookkeeping here, which is natural to see that it didn't take 0.3 seconds to process the data. All in all, the food process, actually, I don't know if I didn't print the timing for the food process. All workers are finished, but I didn't print the time. No, I didn't. Yeah, but all in all, it wasn't that much longer than the other. But yeah, so this is one way to do it. Now, I'm not sure if this is something. So the reason I've said I might have a bug here, but I need to check the documentation again. If you put known here on the consumer side, on the producer side, sorry, and then on the consumer side you check qget if line index is known, and break, well, this works only for the first word. The other will not see it because you put one time known and then you, oh, wait, did I put a loop here? Oh yeah, forget it. Okay, sorry. I wrote it last year, so that was smarter than I thought. So what happens here is that I don't put just one sentinel. I need to put one for worker. Because once they're done, the worker need to actually pull each of them a sentinel to stop. And they will only get one, because once they get it, they will stop, so we're not checking the queue again. So I know that I have 8 workers. They will actually, and we'll actually need to put 8 known at the end to terminate each other and every worker. Is it clear? So I was too fast to read the code. All right, so any question about this? Okay, so today we've seen a lot of stuff, mostly about multiprocessing, some review of threading. The main idea is that mostly if you do parallel programming, you will not need to use multiprocessing. You need multiprocessing if you need to do explicit parallel programming, because most cases this is hidden behind NumPy, TensorFlow, or other libraries that you will use in your programming career. But sometimes you have to actually do this. For example, when you have to manage different devices and you don't have a framework like ROS to use that actually manages the concurrency for you. In these cases, you have to go and dig into these libraries and actually make sure that everything is scheduled and done ordered. It is also very helpful to have seen this because this is something that is not specific to Python, but is actually pretty general in every programming language. Locks, semaphores, concurrency, and so on. So when you actually see you have a bug in NumPy, in one of the parallel implementation within NumPy, you might actually be able to understand what's going on because you have these concepts of locks, of semaphores, and multiprocessing. So it will help you also on that side. But in general, I've used this code a few times for real problems in multiprocessing. Not that often. Usually there's something else you program at a higher level, right? Next time we're going to look into how to construct an API. So completely switch topic again. We're going to look at ways to create a JSON API or a basic web page because you'll need that. I mean, if you have for example, again, a sensor and you want to present the data to another process, you need to actually give access to this sensor. And most of the cases, an HTTP API is the easiest way to do this. Of course, if you need something high performance, you might actually want to do a direct socket or to do distributed programming, and we'll see that at the end of the class. But for now, I think a simple HTTP API works, for example, for our robot. When we have to move the robot, we just call a program to the HTTP method, and it will start a process that will update the position where we want the robot to go. So it's simple, it's very efficient, and for 99% of the cases, all you need. So that's what we'll see next time, and then we'll go on with other topics. I think next we'll have Lucas doing ROS because I'm not here, and then we'll move on and start actually doing NumPy and TensorFlow, more advanced stuff. All right, so that's it for today, and thank you so much.